Algebra 2, Chapter 13, Section 2, Long-Run Behavior of Rational Functions. A rational function can be put into quotient form. So we take the rational function with a numerator and a denominator, and we split it into a quotient plus a remainder over that denominator. The polynomial q is called the quotient, and r is called the remainder. The entire rational function that's left over here, r of x over d of x, is the remainder term. And we can also write this quotient in a different form. The numerator here is equal to the quotient times the denominator plus the remainder. And this just comes from multiplying this whole equation by the denominator. Multiply through by the denominator, it gets lost in both of these places, but gets multiplied by q. So you're left with this. The long-run behavior of a rational function is determined by the leading term of q of x. Okay? And by extension, the ratio of the leading terms of n and d. So if we had 3x squared plus 2x plus 7 over 3x squared plus 3x plus 9, the long-run behavior would just be the ratio of the first two terms, 3x squared over 3x squared. And remember, long-run behavior, we're not near 0, so we can cancel the x. We're just left with 1 over 1 here, which would be, in this case, would be a horizontal asymptote at y equals 1, because when we get really far away from x, y is going to be close to 1, based on this ratio of leading terms. Okay, so if we change this 3 to be a 1, then we would have a ratio of 3x squared over x squared, which would be 3 over 1, which would be a horizontal asymptote at y is 3. And so on. We can take this ratio. If we have an x left over, we won't have a horizontal asymptote. We would have some other kind of asymptote. And we'll talk about this more as we go on here. And so if q of x is 0, the 0 polynomial, then there will be a horizontal asymptote at y equals 0. So the graph would approach the x-axis in such a case. For the rational function 5 plus 3 over x plus 4, graph f and describe its long-run behavior. So here we have a rational function already put into quotient form for us, which simplifies our lives for describing the long-run behavior. So let's draw an x-axis and a y-axis. Here is x, f of x. And then our long-run behavior is going to be given by this quotient. So the long-run behavior will be just the value 5. So we can draw a really bad dashed line. I couldn't get my ruler to make dashed lines. Use a ruler to make that straighter. So as x gets really big, it's going to go to that value. Let's start by putting in x of 1. We'd have 5 plus 3 over 1 plus 4 would be 5 plus 3 over 5, which would be 5.6. 1, 2, 3, 4, 5, somewhere around here. Oh, we should start with 0. Well, if we put in 0, we have 5 and 3/4, which is 5.75. When we put in 2, we'll get 3 over 6, which is 1/2. And so you can see, as we put in values of x, it's just going to get slowly closer and closer to 5. So our graph will look like, almost like a line. It's just going to very slowly approach 5. So the long-run behavior comes from the quotient in the quotient form. It's already in quotient form. And it's from the ratio, or the leading term of q of x. And the leading term of q of x, the quotient, is the constant 5. So that's why we have this y equals 5 long-run behavior. We can use a pretty simple method to put a rational function into quotient form when the degree of the numerator and the degree of the denominator match. In such cases, the quotient will be a constant, and it will be the ratio of the leading coefficients of the numerator and the denominator. Once we know this constant, then we can put the constant in place of the quotient in the form where we have the denominator already multiplied out. We already know the numerator and the denominator when we're trying to put it into rational form. So then we'd have a simple equation here to solve for the unknown here, which is the remainder. So let's do an example. So here we have 30x cubed minus 9x squared plus 1 over 10x cubed minus 3x squared minus 1. So if we think of the ratio of the leading terms, we have 3. That's our k, our constant, our quotient. So we'll have the numerator equals 3 times the denominator plus our remainder, dropping the function notation just for simplicity. The numerator is 30x cubed minus 9x squared plus 1, and 3 times the denominator is 10x cubed minus 3x squared minus 1 plus r. So if we multiply out the 3 times this, we get 30x cubed minus 9x squared minus 3 plus r. Now subtracting 30x cubed from both sides will intentionally, we made this on purpose, cancel those. Adding 9x squared actually cancels the 9x squared. Then adding 3 just leaves us with 4 as the remainder. So here we can write f of x in quotient form as the quotient 3 plus the remainder 4 over the denominator. So that's how we put into quotient form. Let's actually go back and do another example here of putting into quotient form. Let's try this one. Let's try another example here. What if we had to put this into rational form? So we have 18. So we have 8x to the 5th minus 3x squared plus 3x plus 3 over 8x to the 5th minus 3x squared plus 2x plus 2. Okay, so the ratio of the leading terms here is just 1. So our q would be 1. So we'd have the numerator equals 1 times the denominator plus r. Okay? So you can imagine writing 8x to the 5th minus 3x cubed, blah, blah, or minus 3x squared plus 3x plus 3 on the left. Let's just do it. 8x to the 5th for the numerator, 3x squared plus 3x plus 3 is the numerator, equals the quotient q1 times the denominator. 1 times this denominator is just going to be the denominator, plus 2x plus 2. Plus the remainder is what's left over here. So we're trying to find this remainder. So subtracting from both sides, we'll lose the 8x to the 5th. So we'll lose the same minus 3x squared. So we'll subtract 2x from 3x to get x, and 2 from 3 to get 1. And that's what our remainder is, x plus 1. So then we can use the quotient form to write the quotient, to write this in quotient form. So this is a different example. Let's kind of block it off. So we would have the quotient form of this would equal the q of x is 1 plus the remainder x plus 1 over the denominator 8x to the 5th minus 3x squared plus 2x plus 2. And that's what it would be in quotient form for both these two examples. Now let's go on to the next problem. Graph and describe the long-run behavior of the following function. Okay, so here we have our long-run behavior will be determined by the leading term of this quotient, which is just x. So we're going to have a long-run behavior which is going to look like y equals x. This is called a slant asymptote. because we're going to asymptotically approach a slant or a line. Okay, so we already know that about the shape of the graph. That'll help us as we graph. Okay. We also know from looking at the algebraic form here that the denominator is never 0. So our domain is going to be all real numbers for this one. And our y-intercept is going to be 0 plus 1 over 0 plus 1. That would be 1 over 1, and that's 0, which would be negative 1, because 0 minus 1 is negative 1. So we should have at x equals 0, we should have the y value would be negative 1. If we put this function back into factored form, that would help us find any zeros that we might have. So let's think about how to do that. We would multiply this x by x squared plus x squared plus 1 over x squared plus 1 minus all that stuff, which would just be subtracting the numerator from the second thing, since they are the same denominator. So we would distribute, we get x cubed plus x minus 1 over x squared plus 1. And that would give us x minus x is 0, x cubed minus 1 over x squared plus 1. So if you think about where the denominator would be 0 here, it's cubed, we have to have at least one 0. And if we just think about solving x cubed minus 1 equaling 0, that would happen when x is 1. Because you have 1 cubed is 1, 1 minus 1 is 0. So at x of 1, we'll have a 0. And then we know that we have this slant asymptote with a long run behavior. So the graph is going to approach that. And we could plug in more values, but just from this, it's enough to draw a guess of a graph. It's going to be close to here, and it's going to come down, hit the y-intercept, and hit the 0 point, and then get back close again to the slant. And sure enough, that's what the graph looks like if you plug in a bunch of values for x, or use a program that does it for you, and you can look at the graph. Another example with a slant. This one will have slightly different slant. Here we have the rational function given by this expression, and it's already put into quotient form for us. Here's the quotient form. So if we think of the graph of this function, then the long run behavior is going to be given by this line, 2x plus 3. So we can think about what that graph of that line looks like. It has a y-intercept of 3, 1, 2, 3. And it has a slope of 2, so it goes up 2 for every 1x. Okay, so for every 1x it's going to go up 2, or down 2. So the dotted line that we're approaching is going to look like this. If we use a ruler, it'll get a real line. And again, if we find the y-intercept, we get that we have, well, and if we think first, let's think of zeros. So we have a 0 actually when x is 0. So the graph will actually come and touch 0, 0. So when you put in a 0, you have just a 0 in the numerator, we have a 0 out. Okay, so that if we think of factoring this numerator, we'd have x, 2x, actually be x squared on the outside, 2x plus 3. So we'd also have a 0 when 2x plus 3 is 0, which is when x is negative 3 halves. So at negative 1.5, which happens to be exactly on this dotted line, we'll have a 0. And then we have another 0 at 0. So the graph is going to have this funny shape here that's going to have this bump up and back down. And we had x squared at 0. We're going to have a double 0 at 0. So it's going to have the shape of a parabola right here. So it's going to hop over the slant asymptote here and then come back and approach it as we get really, really small. And on this side, it's going to come up and just approach the slant from the bottom. And that's what the shape of our graph will look like. And again, you can plug in numbers and see this shape. Plug in more numbers to make it more intuitive to you, or use the graphing calculator, which does that for you automatically, to see the shape of the graph. Now let's graph this function, 6x to the fourth plus x cubed plus 1 over minus 5x plus 2x squared. So if we think about the long run behavior, we'd have the ratio of the leading terms. And this is a little bit of a trick. On the bottom here we have the polynomial for the denominator not in order. So let's put the x squared first. So the leading terms are now actually in front, and when we divide them, we'll have 3x squared will be our long run behavior. That's a power function, so we'll end up with a long run behavior that's a parabola that's scaled up by 3. So 1, 2, 3, and 1 is where the parabola will go through, and it will go through 9 at 2. So it's going to quickly go way up here, and that's what our long run behavior is going to be shaped like. So our graph will approach a parabola as we get away from the y-axis. And without doing too much more work, the shape of the graph looks kind of like this, and you can graph it yourself to verify that. But there's an asymptote, a vertical asymptote here at 0. It has to do with the fact that there's a 0 here in the denominator and x is 0. And there's another vertical asymptote past 0. I don't think it's right here near 1. It's actually further up. It would be, let's see, when you have, so factoring the denominator, we'd have x times 2x minus 5. So when 2x is 5 at 5 halves. So actually out here at 2.5, which is past where I've shown the graph. So this is really way up here. There's a vertical asymptote. So if we just kind of fudge this a little bit and pull this in 1, 2, 1, 2 at 2.5, that's where we have this other vertical asymptote like this. And we have one also at 0. So in this region, what's the graph doing? It's probably down here somewhere. We'd have to graph it to see. It's probably way down here. So we could actually find that out by putting, say, let's put 1 into the as an x value. So you have 6 plus 1 plus 1 over, which is 8, over minus 5 plus 2 plus 2, which would be 8 over minus 3, which is negative 8/3. So actually it's just it's not far down here somewhere. So there's a little bit of a graph below the x-axis here somewhere between these two asymptotes. So if we want to get a detailed graph, we could use a graphing calculator to do that. But the whole point of this problem is really to show you the long run behavior follows this parabola. So here we have a parabolic long run behavior, or a parabolic asymptote that this is going to approach as x gets really big. Now let's graph x plus 3 over x plus 2 and describe the features that are in the graph. So we have our axes, x and f of x. We have a 0 when x is 3. Sorry, not 3, minus 3. Because the numerator is 0, when the denominator is 0 at minus 2, so we'll have a vertical asymptote at minus 2. Why? It's a vertical asymptote, not a whole, because there's not a 0 at 2 in the numerator. The y-intercept is at 3/2 because x would be 0. So our long run behavior would be x over x, which is 1. So we'll have a horizontal asymptote at y equals 1. So our graph is going to come down from something close to 1, and then hit the 0, and then get, and then get close to this asymptote but not touch it. And it's going to come down from the asymptote after we cross -2, hit the 0, hit the y-intercept at x is 0, which is 1.5, and then approach y equals 1 as x gets really big. So that'll be the shape of our graph. So our important features are the vertical asymptote here at x is -2, a 0 at -3, a y-intercept at 1.5, and a long run behavior, which is a horizontal asymptote at y equals 1. Remember the long run behavior is going to be given by the equation y equals the ratio of the leading terms, x over x. And when we're talking about long run behavior, we're never close to 0. We don't have to worry about dividing by 0. Y equals 1. Let's do another example of graphing and describing the features. So here we have a different one where the numerator is just the number. So we'll have no zeros. So there's no zeros in the numerator. In the denominator we have a triple 0 at 2, a double 0 at 3. 1, 2, 3. That just means we'll have a vertical asymptote. And one of the things you'll notice if you graph these double asymptotes where you have two asymptotes at the same point is that you end up with the graph approaching it from both sides when it's even. So you can remember that because around these asymptotes you're going to have, again, these shapes of power functions, but this time we have power functions that are the negative powers. So the power function x to the minus first looks like this. Remember x to the minus second, you have this shape like this. It's kind of volcano-y shape. So when you have a double powered or a doubled up vertical asymptote, you'll have that similar shape. Now depending on how it might approach the bottom or the top from both. And then at x of -2 we have just 1, 0, so we have another vertical asymptote, but this one will approach from either side like x to the minus first. Our long run behavior will be 25 over x squared. No, x cubed. Okay, which, again, if you remember I said if the numerator has a smaller degree than the denominator, you're going to have a long run behavior of y equals 0. And that's because this long run behavior is really the long run behavior of a hyperbola, which is going to have an asymptote at y equals 0. So if we think about the shape of the power function 25 over x cubed, the shape of it is something like this. Okay, its long run behavior is y equals 0. So our horizontal asymptote is y equals 0. Okay, so we have a vertical asymptote here at x is -2. We have another vertical one which is doubled up. You can call this a double vertical if you want, or you can just leave that off. It's just a vertical asymptote. This helps us when we're graphing to remember those kind of rules of thumb. Vertical asymptote at x equals 3. The horizontal one's at y equals 0. What about zeros? We have no zeros. So the graph is only going to approach 0. It's never going to touch it. What about a y-intercept? When is x 0? We have 25 over 2 and -3 squared, which is 9, which is 25 over 9 times 2 is 18. And 25 and 18 don't have any common numbers together. So we'll just say that's somewhere around here. Something bigger than 1. And our sketch of our graph will be, we're going to come down from this asymptote, never touch 0 because we have no zeros. We're going to have a funny hump that's going to come back up here. And if we graph the actual points, you'll see these points on the hump. I don't have time to go over that, but feel free, in your time, if you want to understand this better, put in 1 and 2 and -1 into the equation and get the actual f values to put on this hump. And then down here, we're going to approach 0 from below, but never get to it. And here, because this is a double, we're going to come back down from up here and approach 0 from above. And never quite get there. And again, like I said, you can feel free to plug in 4 and 5 and get the actual values, and -3 that would go on the curves here. Now, going backwards, let's find a possible formula from a graph using the features of the graph. So here we have a y-intercept at 2. We have a 0 at 2, which just didn't, this is, if you look at the interval here between 1, this is another interval. Didn't get labeled, but that's where that is on the x-axis at 2. Okay, and so we know there's a 0 at 2. We know the long run behavior here, it's got to be y equals 0. So the numerator has to have a smaller degree than the denominator. Okay, so the numerator has to have a 0 at, we'll just go ahead and put a constant here for the y-intercept, which we'll take care of in a minute. The numerator has to have a 0 at 2 to get this 0 in the graph. The denominator is going to have zeros at -1 and 1 to get the zeros, to get the vertical asymptotes we see. And then in order to have a long run behavior of y equals 0, we had to have a degree in the denominator bigger than the numerator, which we've already satisfied. And so we know when x is 0, y is 2, the output is 2 f of x. So we know that 2 is k, x being 0, -2 over 0 plus 1 is 1, 0 minus 1 is -1. So the negatives will cancel. Dividing by 2, we'll get that k is 1 in this case. So the answer would be k is 1. We can just write our formula here, erasing k. And that's the formula for that graph. Let's do another example, finding a formula from a graph. Okay, here we have a long run behavior y equals 2. So our ratio of our leading terms needs to be 2. We have a y-intercept at -4, and we have a 0 at 2. The overall shape looks kind of like a hyperbola shifted around. So we're going to have something like, in the numerator, x -2 to hit this 0. In the denominator, we have a vertical asymptote at, this is at 1. Sorry, at -1. So x plus 1. We need our ratio to be 2 in order to get this long run behavior, and that better make our y-intercept -4. So let's check that. We have, yes, -4. Okay, so both the long run behavior and the y-intercept can help us figure out this constant here, and that's the answer.